A commercial airplane flying at full speed would need 400,000 years just to cross from one edge of this star to the other. If that flight had departed when the first humans walked out of Africa, it would still have hundreds of thousands of years left to travel. This is not a planet. This is not a solar system. This is a single star, and it could swallow Mercury, Venus, Earth, Mars, Jupiter, and Saturn whole. Without touching its own edges, 10 billion suns could vanish inside its body, like raindrops falling into an ocean that has no floor. Its surface gravity is 100,000 times weaker than Earth's. Its outer atmosphere is emptier than the best vacuum any laboratory has ever created. It should not exist. Physics barely allows it. Yet it burns, invisible to every optical telescope ever built, hidden behind 20,000 light-years of cosmic dust so thick that 100 million times less light reaches us than should. And here is what will haunt you. The light we see from this star tonight left its surface when humans were still crossing ice bridges into new continents. The core may have already collapsed. The supernova may have already happened. The largest star ever discovered might already be dead, and we would not know for thousands of years. Tonight, we journey inside a dying titan that defies everything we thought we understood about how large a star can grow. Prepare to have your sense of scale permanently broken. We begin. Let us start with something familiar, something you already know. Our sun, that warm circle you see each morning, is a star roughly 865,000 miles across. You could line up 109 Earths side by side along its middle. You could fit 1.3 million Earths inside its body. By any measure your hands or mind can hold, the sun is enormous. It rules our sky. It feeds every green leaf and warms every ocean. It is the largest object most humans will ever consider in their daily lives. Now, forget everything you think you know about size. Somewhere in the direction of a small, faint constellation called Scutum, roughly 20,000 light-years from where you sit right now, there exists a star called Stephenson, 2-18, and this star does not simply exceed our sun. It humiliates it. It renders the sun invisible. If numbers could scream, the ones describing this object would shatter glass. Stephenson 2-18 measures approximately 2,150 times the radius of our sun. Say that slowly. 2,150 solar radii. Our sun, that massive burning sphere that dominates the entire solar system, could be placed inside this star's diameter over 2,000 times. But diameter is only the beginning of this story. Volume is where the mind truly breaks, because volume does not grow at the same pace as radius. Volume grows with the cube. When you double the width of a ball, you do not double its volume. You multiply it by 8. When you increase a star's radius by 2,150 times, the volume increases by nearly 10 billion times. 10 billion suns could fit inside Stephenson 2-18. Not 10, not 10,000, 10 billion. Written as a number, that is a 1 followed by 10 zeros. If each of those suns were a grain of sand, you would have enough to fill several Olympic swimming pools. And yet, all of those grains combined would only equal the space inside one single star. Let us try to feel this in a way that reaches your bones, rather than just your brain. Imagine our sun as a basketball, a regular basketball, 9.5 inches across, sitting on a court. Now imagine Stephenson 2-18 at the same scale. It would be a sphere roughly 1,700 feet wide. That is taller than the Empire State Building. a basketball next to a ball taller than one of the most famous skyscrapers on Earth. That is the volume difference between our star and the largest known star in the universe. But perhaps the most terrifying way to understand this size is to place the star where our Sun sits, right here, in the center of our solar system. If you put the core of Stephenson 218, where the Sun currently burns, its surface would not stop at Mercury. It would swallow Mercury entirely. Venus would vanish next, gone without a trace. Earth, our home, every city, every mountain, every person who has ever lived, would be deep inside the body of this star. Mars and every robot we have sent to explore it would disappear. The entire asteroid belt, millions of tumbling rocks between Mars and Jupiter, would be consumed. Jupiter itself, a planet so massive it contains more matter than all other planets combined, would be swallowed along with its 79 moons. The surface of Stephenson 218 would extend outward past the orbit of Saturn. Saturn, with its beautiful rings stretching wider than Earth itself, would orbit just barely above the churning surface of this monster. Sometimes, during the closest points of its slightly oval path, Saturn would actually dip into the star's outer atmosphere before swinging back out. Light moves at 670 million miles per hour. Nothing in the universe travels faster. And yet, light needs over 8 hours simply to travel around Stephenson 218 once. Think about that. A beam of light, fast enough to circle Earth 7.5 times in a single second, needs an entire workday just to complete one lap around this star. Here is one more comparison that may keep you awake tonight. A commercial airplane flying at 500 miles per hour would need over 400,000 years to cross from one edge of this star to the other. If that flight had departed when the first modern humans walked out of Africa, it would still have hundreds of thousands of years of travel remaining. The journey would last longer than all of recorded human history multiplied many times over. Now, here is where things become strange. Despite being so impossibly vast, the average density of Stephenson 218 is almost nothing. If you could somehow scoop out a cubic meter of material from the average region of this star, it would contain less matter than a cubic meter of the empty space between planets in our solar system. The star is roughly 10 billion times less dense than our Sun when averaged out. Its outer layers are thinner than the best vacuum scientists can create in any laboratory on Earth. You are looking at an object larger than Saturn's orbit that is, on average, emptier than what we call a vacuum. It is a ghost the size of a solar system, held together by the faintest grip of gravity and the steady flow of energy from deep inside. Some researchers have quietly speculated whether objects this diffuse even deserve the word star in any traditional sense. Their outer edges are not surfaces at all. They are slow fades from something into nothing, like fog dissolving into open air. Where does the star end and space begin? The answer depends entirely on how you choose to draw the line. The photosphere, the depth where light finally escapes, is the official boundary. But in a red supergiant this large, that boundary is so spread out, so gossamer thin, that calling it a surface feels almost dishonest. And there remains a genuine scientific question that no one has fully settled. Is Stephenson 218 truly the largest star in the observable universe, or is it simply the largest we have managed to find so far? Our galaxy holds perhaps 400 billion stars. We have measured the sizes of only a few thousand with real precision. The dust clouds hiding Stephenson 218 for centuries could easily be hiding something even larger. The record could stand for 100 years, or it could fall tomorrow morning when a new infrared survey peers into a region no one has examined closely before. For now, though, the crown belongs to this star. And to understand how we even found it, we need to travel backward in time. To a quiet catalogue entry made by an American astronomer who had no idea what he had stumbled upon, the story begins not with a dramatic discovery, but with a quiet line in a catalogue that almost nobody read. In 1990, an American astronomer named Charles Bruce Stephenson was doing something that sounds almost boring compared to the grandeur of what he unknowingly found. He was surveying the sky in infrared light, documenting bright sources one by one, building a map of objects that glowed at wavelengths human eyes cannot see. His work was systematic, careful, and deeply unglamorous. He was not searching for the largest star in the universe. He was simply counting bright spots in the dark. Among the thousands of entries in his catalogue, one noted a cluster of infrared sources buried deep in the constellation Scutum. He labelled it with the clinical efficiency that science demands. A number, a position, a brightness measurement. Nothing more. Stephenson had no way to determine what these sources truly were. The technology of 1990 could detect infrared glow, but could not pierce deep enough to measure distances, temperatures, or physical sizes of what lay behind the thick curtains of cosmic dust. His catalogue entry for this particular cluster was just another data point, one quiet line among thousands, filed away and largely forgotten. That cluster would eventually be called Stephenson 2, and the largest member within it would receive the name Stephenson 2-18, sometimes written as Stephenson 2-DFK1 in more technical papers. But in 1990, those names carried no weight, no drama, no sense of the impossible object they would come to represent. The constellation Scutum itself plays an important role in this story, and it deserves a moment of attention. Scutum is small and faint. Most stargazers have never heard of it. You will not find it in ancient myths or popular star charts. But when you look towards Scutum during summer nights, you are gazing toward the inner spiral arms of the Milky Way, where stars crowd together in numbers so dense that the sky appears almost milky white with their combined glow. This region contains some of the richest star fields visible from Earth. It is thick with light, thick with worlds, thick with the raw material of stellar existence. But this apparent richness hides an even greater richness behind it. Vast curtains of interstellar dust stretch across this part of the sky like dark veils drawn over a window. These dust clouds block visible light from stars that burn beyond them. For centuries, astronomers staring through optical telescopes saw only the nearest stars in this direction. The true population lurking behind the dust remained completely invisible. It was like standing in a brightly lit room and not knowing that an entire city existed just beyond the frosted glass. Stephenson, too, sits behind one of these veils. The cluster lies roughly 20,000 light-years from Earth, buried in a region where interstellar dust is especially thick. Between us and this cluster, approximately 20 magnitudes of visual extinction block the view. But this is a technical way of saying that visible light from the cluster is dimmed by a factor of roughly 100 million. If you could somehow remove all the dust, Stephenson 218 would suddenly appear as a tremendously bright star in our sky. But with the dust in place, the star does not merely appear faint, it disappears entirely. No optical telescope on Earth or in orbit can see Stephenson 2-18. The star is perfectly invisible to instruments that rely on the kind of light our eyes detect. What finally revealed this hidden giant was infrared light, radiation with wavelengths longer than what human eyes can sense. But that story belongs to a later part of our journey. For now, what matters is the cluster itself. because Stephenson 218 did not form alone. It was born inside a family of giants. Stephenson 2 contains at least 26 red supergiant stars. 26. To find even one red supergiant is noteworthy. To find 26 of them gathered in a single cluster is extraordinary. The total mass of this cluster is estimated somewhere between 40,000 and 100,000 solar masses, all packed into a region spanning roughly 6 light-years across. To feel that distance, consider that the nearest star to our Sun, Proxima Centauri, sits about 4.24 light-years away. The entire Stephenson 2 cluster would fit comfortably in the gap between our solar system and our closest neighboring star. And yet, within that modest stretch of space, dozens of the most extreme stars in our galaxy burn together, shoulder to shoulder by cosmic standards. Why does this cluster contain so many red supergiants at the same time? The answer involves timing and the brief nature of stellar death. Massive stars live fast. A star 20 times heavier than our Sun exhausts its hydrogen fuel in roughly 10 million years, compared to the Sun's 10 billion. The stars in Stephenson 2 likely formed together around 20 million years ago, born from the same collapsing cloud of gas during some ancient burst of star formation. Perhaps a passing shockwave from a distant supernova compressed the cloud. Perhaps the slow grinding of galactic spiral arms squeezed it past the tipping point. Whatever the trigger, dozens of massive stars ignited within a relatively short window of cosmic time. Now, 20 million years later, the most massive among them have exhausted their hydrogen. Their cores have contracted. Their outer layers have swollen to monstrous proportions. They have entered the red supergiant phase, the brief, bloated final chapter before death. We are witnessing Stephenson 2 during a narrow window when its heaviest members have become giants but have not yet exploded as supernovae. In another million years, perhaps less, many of these stars will have detonated, leaving behind neutron stars or black holes. The cluster we observe today is a snapshot of a fleeting moment in stellar evolution, caught at precisely the right time. This timing dependence makes clusters like Stephenson 2 inherently rare. The red supergiant phase lasts only a few 100,000 years, a blink compared to total stellar lifetimes. Finding 26 such stars in one location requires catching a cluster during exactly the right epoch. It is like photographing a fireworks display at the precise instant when every shell has burst but none has yet faded. One moment earlier and the shells are still rising. One moment later and the sky is dark again. Here is something that scientists still debate quietly among themselves. The exact number of red supergiants in Stephenson 2 remains uncertain. Some surveys count 26. Others suggest the number could be higher, with additional members hidden behind even thicker dust or confused with foreground stars that only appear to belong to the cluster. The boundaries of the cluster itself are not perfectly defined. Stars at the edges might be true members, or they might be unrelated objects that happen to lie along the same line of sight. Sorting genuine members from imposters requires precise distance measurements, and at 20,000 light-years, through heavy dust, precision is hard to come by. What is not debated is that Stephenson 2 ranks among the most massive and extraordinary stellar clusters in the entire Milky Way. And within this congregation of giants, one star rises above all others. Stephenson 218 dominates the cluster like a mountain among hills. But to confirm that dominance, astronomers needed to solve one of the hardest problems in all of science: measuring the true size of something impossibly far away and completely invisible to the naked eye. How do you measure something you cannot touch, cannot visit, and cannot even see with your own eyes? This is the problem that faced every astronomer who wanted to understand the true size of Stephenson, 218. The star sits 20,000 light-years away, buried behind dust so thick that it erases the star from visible existence. You cannot point a ruler at it. You cannot fly a spacecraft to it. You cannot wrap a tape measure around its belly. Everything we know about the dimensions of this star comes from indirect methods, each one brilliant and each one carrying its own weight of uncertainty. The challenge is almost absurd when you think about it clearly. Imagine someone asked you to measure the width of a single coin sitting on a table in a city on the opposite side of the Earth, not with your hands, not with a magnifying glass, but using only a telescope from where you currently stand. The coin would appear so tiny, so impossibly small against the distance, that distinguishing it from a simple dot would push any instrument to its absolute limits. Now make the problem harder. Put a thick fog between you and the coin, a fog so dense that ordinary light cannot pass through it. That is roughly what astronomers face when trying to measure Stephenson 2-18. The first tool in their kit is something called angular diameter. This describes how large an object appears from Earth, expressed in unimaginably small fractions of a degree. 1 degree is already small. Hold your pinky finger at arm's length and it covers about 1 degree of sky. Now divide that single degree into 3,600 equal parts. Each part is called an arcsecond. The full moon spans about 1,800 arcseconds across. A human hair held at arm's length covers roughly 60 arcseconds. Stars at cosmic distances appear so tiny that their angular diameters are measured in milliarcseconds, thousandths of an arcsecond. Some require measurements in microarcseconds, millionths of an arcsecond. Capturing such impossibly small angles demands the most advanced infrared interferometers ever built by human hands. But here is the critical problem. Angular diameter alone tells you almost nothing about true physical size. A small star sitting nearby and a giant star sitting far away can look exactly the same size from Earth. Both might cover the same tiny angle of sky. To convert that angle into actual physical width, you need a second piece of information: distance. Without knowing how far away the object sits, its apparent size is meaningless. A basketball held close to your face and a house seen from a mile away can cover the same angle in your vision. You need both measurements, angle, and distance working together to calculate the real dimensions. This two-step process introduces uncertainty at every stage. Measure the angle imprecisely and your size calculation drifts. Measure the distance wrong and your size calculation drifts even further. For nearby stars, both measurements can be made with reasonable confidence. For a star buried behind 20,000 light-years of galactic dust, each measurement becomes extraordinarily difficult, and the errors compound on top of each other. Distance measurement for stars relies primarily on a method called parallax. The idea is beautifully simple. As Earth orbits the Sun over the course of a year, our viewing position shifts. We look at a star from one side of our orbit in January and from the opposite side in July. The star appears to shift slightly against the background of more distant stars, just as your thumb appears to jump when you look at it first with one eye, then the other. By measuring how much the star appears to shift, astronomers can calculate its distance using basic geometry. Closer stars shift more, distant stars shift less. The math is straightforward. The measurement is anything but. The Gaia Space Observatory transformed this ancient technique into something extraordinary. Launched by the European Space Agency in 2013, Gaia tracks the positions of nearly 2 billion stars with precision that would have seemed like science fiction just a generation ago. By observing each star repeatedly over years of operation, Gaia measures parallax shifts so tiny that they reveal distances spanning tens of thousands of light years. Before Gaia, parallax measurements were reliable only for relatively nearby stars. Gaia pushed the boundary outward by orders of magnitude, making it possible to estimate distances even for objects as remote and obscured as Stephenson 2-18. But Gaia's measurements for heavily obscured stars still carry significant uncertainty. The dust between Earth and Stephenson 2-18 does not merely block light. It also slightly bends and scatters the infrared light that does get through, introducing subtle distortions in the apparent position of the star. These distortions add noise to the parallax measurement, making the distance calculation less precise than it would be for a star in a clear line of sight. Different research teams analyzing the same Gaia data sometimes arrive at slightly different distance estimates, which in turn produce different size calculations for the star. When astronomers finally combined infrared brightness measurements with careful distance calculations from Gaia and other sources, the numbers that emerged seemed almost unreasonable. Stephenson 2-18 measured approximately 2,150 solar radii, but this figure comes wrapped in significant uncertainty. Some analyses suggest the star could be as small as 1,800 solar radii. Others push the measurement as high as 2,400. The scientific consensus currently clusters around 2,000 to 2,200 solar radii, but researchers continue refining these numbers as instruments improve and new data arrives. Here is a detail that complicates things even further, one that challenges the very idea of measuring a star's size with a single number. Red supergiants pulsate. They breathe in and out like slow cosmic lungs, expanding and contracting over periods lasting hundreds or even thousands of days. Stephenson 2-18 probably pulsates over cycles spanning several years. During maximum expansion, it may exceed 2,200 solar radii. During minimum contraction, it may shrink below 2,000. The size you measure depends on when you happen to look. A star observed at its most bloated moment will appear significantly larger than the same star observed months or years later when it has pulled itself inward. And then there is the question of where the star actually ends. Red supergiants do not have sharp edges like a planet or a billiard ball. Their outer atmospheres fade gradually from thin stellar material into even thinner circumstellar gas that eventually blends into the emptiness of interstellar space. There is no wall, no boundary line, no coastline where star meets void. Astronomers use the photosphere as their official edge. The depth where the star becomes opaque and light can no longer escape freely. But for a star this enormous and this diffuse, the photosphere itself is extraordinarily vague, more like a slow fog than a solid barrier. Some scientists have raised the quiet question of whether our current measurement tools are truly capable of pinning down the size of something this extreme with the precision the public assumes. The error bars on Stephenson. 2-18's radius are not small footnotes. They represent genuine scientific humility, an honest admission that measuring the width of a pulsating, edgeless, dust-shrouded object 20,000 light-years away is one of the hardest tasks in all of astronomy. Despite all of this uncertainty, the evidence converges powerfully. Multiple independent teams using different instruments and different analytical methods all arrive at the same basic conclusion. Stephenson 2-18 exceeds 2,000 solar radii. The precise number remains a moving target, but the fundamental fact stands firm. This star is larger than anything else we have found in the observable universe. The measurements are real, the methods are sound, and the object they describe is beyond anything human. intuition was ever built to grasp, but all of those measurements depended on one crucial breakthrough: learning to see in a kind of light that human eyes were never designed to detect. There is a kind of light your eyes will never see. It surrounds you right now, radiating from your body, from the walls of your room, from every warm object in your world. It is called infrared light, and it operates at wavelengths longer than the red edge of what human vision can detect. You cannot see it, but it is always there, and without it, the largest star in the universe would have remained hidden forever. The problem with seeing Stephenson 218 is not distance alone. 20,000 light-years is far, but astronomers routinely study objects millions or even billions of light-years away. The real obstacle is dust. Between Earth and this star lies a vast ocean of interstellar dust particles, tiny grains of carbon and silicates, each measuring roughly 1 micrometer across, about 1/100th the width of a human hair. These grains float through interstellar space in enormous clouds, concentrated most heavily along the plane of our galaxy, and especially thick in the direction of Scutum, where the line of sight passes through multiple spiral arms stacked behind one another. When visible light from Stephenson 218 encounters these dust grains, something very specific happens. The wavelength of visible light is roughly similar in size to the dust grains themselves. When electromagnetic radiation meets particles of comparable size, scattering occurs with brutal efficiency. The light bounces, deflects, absorbs. Shorter wavelengths scatter even more aggressively than longer ones, which is the same physics that makes our daytime sky blue and our sunsets red. Blue light from the sun scatters in all directions when it hits air molecules, painting the sky. Red light, with its longer wavelength, pushes through more easily, giving sunsets their warm glow. Now scale this effect up enormously. The dust between us and Stephenson 218 does not merely tint the star's light slightly red, it annihilates it. 20 magnitudes of visual extinction means the star appears 100 million times fainter in visible light than it would without any dust. 100 million times. Imagine trying to see a candle through a fog so thick that its light dims by a factor of 100 million before reaching your eye. The candle would be utterly invisible. Not faint, not dim. Gone. That is what happens to every visible photon that Stephenson 218 sends in our direction. The cosmic fog devours them completely. No optical telescope ever built, on Earth or in space, can see this star. Not Hubble. Not any ground-based observatory, regardless of its mirror size or detector sensitivity. In visible wavelengths, Stephenson 2-18 simply does not exist from our perspective. It is perfectly erased from the visible sky, but infrared light plays by different rules. Infrared wavelengths range from about 1 micrometer to hundreds of micrometers, several times longer than visible light. When these longer waves encounter the same micrometer-sized dust grains, the scattering is dramatically weaker. The mathematical relationship between wavelength and scattering efficiency means that light at 2 micrometers penetrates dust roughly 10 times more effectively than light at half a micrometer in the blue part of the visible spectrum. The cosmic fog that swallows visible light becomes semi-transparent at infrared wavelengths. Not perfectly clear. Some absorption still occurs, but enough infrared radiation passes through to reveal what lies behind the veil. This principle transformed astronomy over the past half-century. Infrared telescopes see through cosmic dust the way X-rays see through human flesh. The bones of the galaxy, its hidden star clusters, its buried stellar nurseries, its secret populations of giant stars, all become visible when you shift your eyes from optical to infrared wavelengths. Hundreds of millions of stars exist in our galaxy that no optical telescope will ever detect because the intervening dust is simply too thick. Stephenson 218 is one particularly spectacular member of this hidden population. The technology to exploit this principle developed gradually over decades. Early infrared detectors in the 1970s and 1980s were crude by modern standards, sensitive enough to detect bright infrared sources but unable to measure them with the precision needed for serious scientific analysis. When Charles Bruce Stephenson compiled his 1990 catalogue, he was working with these early tools. He could note that bright infrared sources existed in certain positions, but could not determine their true nature. The 2 micron. All Sky survey, completed in 2001, represented a major step forward. This survey systematically mapped the entire sky at infrared wavelengths near 2 micrometers, cataloguing millions of sources with improved accuracy. Stars in the Stephenson 2 cluster received better brightness measurements, though their physical properties remained poorly understood. Then came the Spitzer Space Telescope, launched in 2003, which observed at mid-infrared wavelengths that cannot be detected from Earth's surface because our own atmosphere absorbs them. Spitzer revealed additional details about the cluster environment, peeling back another layer of the cosmic veil. But the true breakthrough required combining multiple capabilities that only converged in the 2000s. Gaia provided revolutionary distance measurements. Ground-based infrared interferometers achieved angular resolution fine enough to constrain stellar diameters even for distant objects. Sophisticated atmospheric models developed by theoretical astrophysicists allowed scientists to connect observed brightness and temperature to physical size through established mathematical relationships. The convergence of all these tools finally produced the modern understanding of Stephenson 2-18 as the largest known star. Stephenson 2-18 shines brightest at wavelengths around 2 micrometers, deep in the infrared spectrum. At these wavelengths, the dust that blocks 99.9999% of its visible light removes only a fraction of its infrared emission. The star that is utterly invisible through an optical telescope becomes one of the brightest sources in the infrared sky at its particular wavelength. This dramatic difference between optical and infrared appearance immediately flags the object as extraordinary, worthy of detailed investigation. Here is something odd and beautiful to consider. The reason Stephenson 218 naturally peaks in infrared has nothing to do with dust. It relates to the star's own temperature. All objects emit thermal radiation with a spectrum determined by how hot they are. Hotter objects emit radiation at shorter wavelengths, peaking in blue or ultraviolet. Cooler objects emit at longer wavelengths, peaking in infrared. Red supergiants have surface temperatures around 3000 to 4000 Kelvin. It's cool by stellar standards. Our Sun's surface reaches 5778 Kelvin. Blue supergiants exceed 20,000 Kelvin. The cool surface of Stephenson 218 shifts its peak emission naturally toward infrared wavelengths. It is an infrared object by nature, not just by circumstance. Even without any intervening dust, most of this star's light would be invisible to human eyes. We would see a deep red glow, but the majority of its energy output would pour into wavelengths we cannot perceive. There is an ongoing debate among infrared astronomers about whether current surveys have truly mapped the most obscured regions of our galaxy thoroughly enough to claim we have found the largest star. Some researchers argue that existing infrared surveys still lack the sensitivity and resolution needed to fully characterize stellar populations behind the thickest dust concentrations near the galactic center. Future facilities like the extremely large telescope, with its 39-meter mirror and advanced adaptive optics, may reveal entirely new populations of stars hidden behind dust clouds even thicker than those concealing Stephenson 2. The cosmos may still hold secrets that even infrared eyes have not yet pierced, but what infrared astronomy has already revealed deserves a portrait of its own. Because the star that emerged from behind the dust is not merely large, it is one of the strangest objects physics permits. Close your eyes for a moment and imagine standing on a planet orbiting somewhere near this star. Not dangerously close, just near enough to see it fill your sky. What would you see? Not the bright yellow-white disk you know from Earth mornings. Instead, a vast wall of dim red light stretching from horizon to horizon, covering half your entire visual field. The sky would not be blue. It would glow with an eerie crimson wash, a light so spread out that it feels less like a sun and more like the inside of a furnace seen through dark glass. Day and night, as you understand them, would lose all meaning. When your sun fills half your sky, there is no sunrise, no sunset. There is only the red. This is the paradox of Stephenson 2.18. It is one of the most luminous stars ever discovered, pouring out energy equivalent to 440,000 suns combined. Some estimates push this number even higher, to 630,000 solar luminosities. By any accounting, this star radiates more energy than almost anything else in our galaxy. And yet, if you could stand near it and look at its surface, each square meter of that surface would actually appear dimmer than each square meter of our sun. How is this possible? The answer lives inside a beautiful equation called the Stefan-Boltzmann law, and understanding it reveals something deeply strange about the nature of enormous stars. This law describes how the total energy a star radiates depends on two things: its surface temperature and its total surface area. The energy output scales with temperature raised to the fourth power and with surface area directly. Both matter, but they can pull in opposite directions. Stephenson 2.18 has a surface temperature of approximately 3,200 Kelvin. Our sun burns at 5,778 Kelvin. That means our sun is nearly twice as hot at its surface. Because the Stefan-Boltzmann law raises temperature to the fourth power, this temperature difference has enormous consequences. Each square meter of our sun's surface radiates far more energy than each square meter of Stephenson 2.18's surface. The cooler star glows less intensely at every point across its face, but surface area tells the opposite story. Stephenson 2-18 has a radius roughly 2,150 times greater than our sun. Surface area scales with the square of the radius. When you square 2,150, you get a surface area more than 4 million times larger than our sun's. 4 million times more surface, each square meter contributing its share of energy. Even though each meter glows more dimly than our sun's surface, the sheer number of meters overwhelms the difference in temperature. The total output reaches hundreds of thousands of solar luminosities despite the relatively cool surface. Enormous total brightness. Dim surface brightness. Both facts are true simultaneously, and together they create the strange visual experience of a star that fills your sky with a soft red light, rather than a blinding white blaze. At that cool surface temperature, something unexpected happens. Molecules form, not deep inside the star, where temperatures reach hundreds of millions of degrees and no molecule could survive for an instant, but at the very outer edge, in the thin atmospheric layers where temperatures drop low enough for atoms to bond together. Spectroscopic observations of red supergiants reveal titanium oxide, water vapor, and carbon monoxide molecules floating in their outer atmospheres. These are chemicals you might associate with geology or chemistry labs. not with the surface of a star. Yet they exist there, stable enough to leave their fingerprints in the light that escapes into space. These molecules would be instantly destroyed on our Sun's surface, where 5,700 degree temperatures rip apart any molecular bond. But at 3,200 Kelvin, certain tough molecules can survive. Their presence affects how light escapes from the star, creating dark absorption lines in the spectrum that astronomers use to measure temperature, composition, and motion. The titanium oxide bands, in particular, give red supergiants their characteristic deep red color. Without these molecules, the star would look different and would be far harder to study from across the galaxy. Now, consider the density at this strange surface. While the core of Stephenson 218 remains extraordinarily dense, with material packed tighter than anything on Earth, the outer atmosphere is the opposite. At the photosphere, where the visible surface is defined, the density drops to roughly 1/billionth of Earth's atmospheric density at sea level. 1/billionth. The air you are breathing right now is 1,000,000,000 times denser than the glowing surface of the largest known star. The tenuous material forming that visible surface would be considered a better vacuum than most laboratory equipment on Earth can produce. High vacuum chambers used for scientific experiments typically achieve densities millions of times higher than the density at Stephenson 218's photosphere. Yet this incredibly thin material produces the light we observe. Photons generated in deeper, hotter layers scatter and absorb through this extended atmosphere before finally escaping into space. The long path through gossamer-thin material allows even weak absorption processes to shape the emerging radiation significantly. Light takes its time leaving, interacting gently with atoms and molecules along the way, picking up the spectral signatures that tell astronomers what the atmosphere contains. The sound inside this star deserves a moment of quiet wonder. Sound waves in stellar material travel at speeds determined by temperature and density. In the thin outer layers of Stephenson 218, sound moves at roughly a few kilometers per second. Given the immense diameter of this star, an acoustic wave would take weeks to travel from one side to the other. If something dramatic happened on one side of the star, a sudden burst of convection, a pulsation wave, the other side would not know about it for weeks. The star is so large that its own body cannot communicate with itself on any timescale that matters to human observation. Different regions of the star essentially live in isolation from each other, each responding to local conditions without any awareness of what happens on the opposite side. Here is a speculative thought that some astrophysicists have entertained privately. At such extreme dimensions and such low densities, the boundary between what counts as a star and what counts as a very hot, very large nebula becomes philosophically blurry. Stephenson 2-18 occupies a strange middle ground, an object too organized to be a simple cloud of gas, but too diffuse to match our instinctive image of a star as a solid, sharply bounded sphere of fire. It challenges our categories in ways that reveal how much our understanding of stars was shaped by studying objects far more compact and well-defined. There remains an unresolved scientific question about the luminosity of Stephenson 2-18 that quietly divides researchers. The range between 440,000 and 630,000 solar luminosities is not a small uncertainty. It represents nearly a 50% spread, driven by differing assumptions about distance, dust extinction corrections, and how to model the star's extended atmosphere. And different teams using different dust models arrive at genuinely different luminosity estimates. Until distance measurements improve further and atmospheric models become more sophisticated, The true energy output of this star will remain an open question, known in broad strokes but blurred in fine detail. What is not blurred is the basic portrait that emerges from all observations combined. Stephenson 218 is cool, colossal, impossibly diffuse, and extraordinarily luminous when all its dim surface is counted together. It is a star that breaks every intuition formed by living under a compact, hot, well-behaved sun. But this strange giant was not always strange. It was not always giant. Long ago it was something entirely different, something compact and fierce and blue. To understand how it became the monster we observe today, we must rewind millions of years and watch a very different kind of star ignite for the first time. Every giant was once small. Every monster had a beginning, and the beginning of Stephenson. 218 looked nothing like the bloated crimson titan we observe today. Roughly 20 million years ago, in a dense region of the Milky Way, where gas and dust collected in thick, cold clouds, gravity began to win a slow battle against pressure. A massive clump of hydrogen gas, perhaps triggered by the shockwave of a nearby supernova, or the grinding compression of a passing spiral arm, started collapsing inward under its own weight. The cloud fell toward its own center, heating as it compressed, glowing faintly at first, then more intensely as temperatures climbed. When the core of this collapsing ball reached approximately 10 million Kelvin, something extraordinary happened. Hydrogen nuclei, stripped of their electrons and moving at tremendous speeds, began slamming into each other hard enough to overcome their natural electrical repulsion. They fused. 4 hydrogen nuclei merged into one helium nucleus, and in that merging, a tiny amount of mass disappeared, not destroyed, transformed, converted into pure energy according to Einstein's equation, E equals mc squared. That tiny mass difference, roughly 0.7% of the original hydrogen mass, became the light and heat that would power this star for millions of years. A star was born, and it was not red. It was blue. The young Stephenson 218 entered the universe as a brilliant blue supergiant, blazing with surface temperatures exceeding 20,000 Kelvin, more than 3 times hotter than our Sun's surface. It radiated primarily in ultraviolet wavelengths, light so energetic that it would be invisible to human eyes, but deadly to any unprotected biology nearby. Planets orbiting within a light year of this young furnace would have been bathed in sterilizing radiation that would prevent any chemistry resembling life as we know it. This was not a gentle star. It was a weapon of light. Its luminosity already exceeded tens of thousands of suns during this early phase. Yet physically, it was relatively compact, perhaps 10 to 20 times our sun's diameter. A tight, fierce nuclear engine radiating energy at rates millions of times greater per unit volume than what it would eventually produce as a red supergiant. All that power concentrated into a body small enough to fit comfortably inside Mercury's orbit. The fate of this star was sealed at the moment of its birth by a single number: mass. Stephenson 2-18 began with an initial mass estimated between 25 and 40 solar masses. This placed it among the rarest stars in the galaxy. Stars containing more than 8 solar masses represent less than 1% of all stars born. Stars exceeding 20 solar masses are rarer still, perhaps 1 in 1,000. Stars approaching 40 solar masses sit at the extreme tail of the stellar mass distribution, so uncommon that astronomers must survey enormous volumes of space to find meaningful samples. This initial mass determined everything that would follow. Every phase of evolution, and every transformation, every eventual death was written into the star's destiny from the instant fusion ignited. Know a star's birth mass, and you can predict its entire life story with remarkable accuracy. The physics is ruthless in its precision. Massive stars live fast and die young. This seems counterintuitive. You might expect that a star with 30 times more fuel than the Sun would live 30 times longer. The opposite is true. Massive stars burn through their hydrogen reserves so rapidly that they live far shorter lives despite their greater fuel supply. Our Sun will burn hydrogen for approximately 10 billion years. It has already completed roughly half this journey. A star like the young Stephenson 218 exhausted its hydrogen in a mere 10 to 15 million years. Why such a dramatic difference? The answer lies in gravity and temperature. More massive stars have stronger gravity, which compresses their cores to higher densities and temperatures. The core temperature of young Stephenson 2 to 18 exceeded 40 million Kelvin during its main sequence phase, roughly 3 times hotter than our Sun's core temperature of 15 million Kelvin. This seemingly modest temperature difference has enormous consequences because nuclear fusion rates are extraordinarily sensitive to temperature. The primary fusion process in massive stars differs from the one operating inside our Sun. While the Sun fuses hydrogen through what physicists call the proton-proton chain, massive stars predominantly use a different pathway called the carbon-nitrogen-oxygen cycle, often shortened to the CNO cycle. This process uses carbon, nitrogen, and oxygen nuclei as catalysts, allowing hydrogen fusion to proceed at rates far exceeding the proton-proton chain. The CNO cycle's reaction rate scales approximately with the 16th power of temperature. The 16th power. This means that even small increases in temperature produce enormous increases in the rate at which hydrogen is consumed. Double the core temperature and the fusion rate does not merely double, it increases by a factor of roughly 65,000. This temperature sensitivity is why massive stars squander their fuel so recklessly. They have more fuel than the Sun, but they burn through it at rates that vastly outpace their greater supply. A star 30 times more massive than the Sun does not live 30 times longer. It lives roughly 1,000th as long. The inheritance is larger, but the spending is catastrophically faster. During its main sequence phase, lasting perhaps 12 million years, the young Stephenson 218 maintained a delicate balance between two opposing forces. Gravity pulled every particle of the star inward, trying to crush it into its own center. Radiation pressure from the nuclear furnace pushed outward, supporting the star against collapse. These two forces locked in eternal combat, perfectly balanced, creating what physicists call hydrostatic equilibrium. As long as hydrogen fuel remained available in the core, this balance held. The star maintained its compact hot blue form, pouring energy into space at tremendous rates while gravity waited patiently for the fuel to run out. And fuel always runs out, no matter how vast the supply. The hydrogen in the core slowly converted to helium, accumulating like ash in a fireplace. Unlike hydrogen, helium requires much higher temperatures to fuse because helium nuclei carry greater positive electrical charge and repel each other more strongly. Temperatures exceeding 100 million Kelvin are needed before helium nuclei can approach closely enough for the strong nuclear force to grab them and pull them together. The core gradually transformed from active nuclear reactor to inert ball of helium ash, growing heavier and denser while the zone of active hydrogen burning shrank around it. Here is a speculative thought that some theorists have explored. During its blue supergiant phase, Stephenson 218 may have had companion stars orbiting nearby, binary or even triple systems being common among massive stars. If so, the intense radiation and stellar winds from the young Stephenson 2-18 could have stripped material from those companions or even disrupted their orbits entirely. Whether any companions survived to witness the star's later transformation into a red supergiant remains unknown. The dust and distance that hide this star also hide its possible history as part of a multiple star system. What is not speculative is what happened next. When hydrogen exhaustion finally struck the core, the delicate equilibrium that had held for 12 million years broke apart. Without nuclear energy to fight gravity, the helium core began to contract. And as it contracted, something started happening to the outer layers of the star that would eventually produce the largest stellar object ever discovered. The compact blue furnace began its long, unstoppable transformation into something vast, cool, and red the moment hydrogen ran out in the core. The star began to change in ways that would have seemed impossible to predict from its compact blue youth. Without nuclear energy holding it up from the center, the helium core contracted under gravity. There was nothing stopping it. No energy source, no outward push, just dead weight falling inward. As it contracted, gravitational potential energy converted to heat. The core grew hotter and denser, squeezing itself smaller while radiating energy into the layers above. This contraction did something unexpected to the region just outside the dying core. A thin shell of hydrogen surrounding the helium ash reached temperatures high enough to ignite its own fusion reactions. A new nuclear burning zone sparked to life, not in the center of the star where fusion had always lived, but in a ring wrapped around the inert core like a belt of fire. This shell-burning phase marked the beginning of the most dramatic transformation in the star's life. The energy released by this hydrogen shell exceeded what the original core fusion had produced. This seems strange since the shell contained less material than the old core. But the shell burned at higher temperatures and greater densities than the core ever reached during main sequence life. The reaction rates accelerated. Energy poured outward into the layers above at rates the star had never experienced before. The outer layers of the star responded to this flood of energy in the only way physics allowed. They expanded. Material pushed outward against gravity, swelling the star's body to dimensions that grew week by week, century by century. The surface retreated away from the center as interior layers rearranged themselves to accommodate the new pattern of energy generation. The star began to cool as its surface spread across ever larger volumes. Hot blue light gave way to warm orange, then to deep red, as surface temperatures dropped from over 20,000 Kelvin to roughly 3,000. The compact blue supergiant was becoming a red supergiant, and for Stephenson 218, this expansion would continue far beyond what occurs in ordinary stars, pushing the boundaries of what stellar physics permits. The physics driving this extreme expansion involves how energy moves through the interior of a star. In the deep core and surrounding regions, energy travels outward as radiation. Photons bounce repeatedly off dense material in a process called radiative diffusion. Each photon travels only a short distance before hitting an electron or atomic nucleus and bouncing in a random direction. The journey from core to surface involves countless such collisions, with photons effectively stumbling blindly through the stellar interior. In our Sun, this random walk takes roughly 170,000 years for energy generated in the core to finally reach the surface. But in the cooler outer regions of massive, evolved stars, a different energy transport mechanism takes over. Convection. Giant cells of hot material rise from deeper layers, carrying heat upward the way boiling water rises in a pot on a stove. The hot material reaches cooler regions above, dumps its heat, then sinks back down to collect more. This convective transport moves energy far more efficiently than radiation in regions where the temperature changes steeply with depth. The transition from radiative to convective energy transport profoundly affects how large a star can grow. Convective envelopes can expand nearly without limit if enough energy flows through them from below. The stellar surface retreats outward, cooling as it stretches, eventually reaching temperatures where molecules can form in the outer atmosphere. The expansion continues until a new balance establishes itself, with energy generated in the burning shells transported outward through the convective envelope and radiated into space from the cool, extended surface. For the most massive stars in this evolutionary phase, that balance occurs at dimensions measured in thousands of solar radii. Stephenson 2-18 represents one of the most extreme examples of this process ever observed. The convection cells operating inside this star dwarf anything in our solar system. Individual cells can span several astronomical units, each one larger than the distance from Earth to the Sun. 1 astronomical unit equals roughly 93 million miles. Convection cells on Stephenson 2-18 probably span distances larger than Jupiter's orbit, which lies over 5 astronomical units from the Sun. These massive bubbles of rising and sinking material appear as bright and dark patches on the surface. Bright patches represent hot material welling up from below. Dark patches represent cooler material sinking back into the interior. The contrast between rising and falling regions creates a mottled, uneven surface that shifts and rearranges over months to years. We cannot observe these convection patterns directly on Stephenson 2-18 because of its great distance and the intervening dust. But observations of closer red supergiants reveal exactly this kind of large-scale surface structure. Betelgeuse, located only about 700 light-years from Earth in the constellation Orion, shows convection cells roughly the size of Earth's orbit when studied with advanced imaging techniques. Stephenson 2-18 almost certainly displays similar features on even grander scales, vast bubbling continents of hot gas rising and falling across a surface larger than Saturn's orbit. The mass loss from this bloated giant proceeds through multiple mechanisms working simultaneously. As temperatures in the extended outer atmosphere drop below roughly 1500 Kelvin, silicate and carbon-rich dust grains condense from the gas like snowflakes forming in cold air. These tiny solid particles absorb starlight efficiently and feel strong radiation pressure pushing them outward. The accelerating dust grains drag gas along with them through collisions, creating stellar winds that carry material steadily away from the star. This dust-driven wind erodes the stellar envelope continuously over thousands of years. Pulsation adds another layer of mass loss. When the star contracts during its breathing cycle, the compression sends waves propagating outward through the atmosphere. These waves steepen into shocks as they travel through regions of decreasing density, accelerating material to speeds exceeding the local escape velocity and launching discrete shells of gas into space. The enormous convection cells contribute as well, lifting material to heights where the star's feeble surface gravity can no longer hold it. The surface gravity of Stephenson 2-18 is perhaps 100,000 times weaker than Earth's, making escape relatively easy for material that reaches the outer atmosphere. The combined effect of these mechanisms produces mass loss rates millions of times greater than our Sun's solar wind. The Sun loses roughly 1 million tons of material every second through its solar wind. Stephenson 2-18 probably loses the equivalent of the Sun's entire mass every few thousand to 10,000 years. Over its remaining lifetime, perhaps a few 100,000 years before its core collapses, it will shed several solar masses into surrounding space, creating shells and clouds of ejected material that glow faintly in infrared light at various distances from the star. Here is a speculative idea that some researchers have quietly considered. Could the extreme mass loss from a star this large eventually strip enough material away to prevent it from exploding as a supernova altogether? If enough envelope mass is removed, the remaining star might evolve differently than standard models predict. Most theorists believe the core mass is already too large for this to matter, that the iron core will grow regardless. But the interaction between mass loss rates and core evolution in the most extreme red supergiants remains an area where models carry genuine uncertainty. What is certain is that deep beneath this enormous, slowly evaporating envelope, the core has been busy. While the outer layers expanded to record-breaking dimensions, the interior has been racing through a series of nuclear burning stages, each one faster and more desperate than the last. The star is building something terrifying at its center, an onion of nuclear ash, layer upon layer, driving toward an ending that nothing can prevent. While the outer layers of Stephenson 218 expanded to dimensions that could swallow most of our solar system, the core was living an entirely different life. Down in the deepest interior, hidden beneath billions of miles of thin glowing atmosphere, a series of nuclear transformations unfolded with increasing speed and increasing desperation. Each stage burned hotter, consumed fuel faster, and produced heavier elements than the one before. The star was building itself a death sentence, one atomic layer at a time. After hydrogen exhaustion triggered the Great Expansion, the helium core continued contracting under gravity until its temperature crossed 100 million Kelvin. At that threshold, something remarkable happened. Helium nuclei began fusing together through a process nuclear physicists call the triple alpha process. The name refers to alpha particles, the physics term for helium nuclei, each containing 2 protons and 2 neutrons. 3 of these particles must combine nearly simultaneously to form a single carbon nucleus. The odds of this happening are extraordinarily small, which is why temperatures must reach such extreme levels before it proceeds at meaningful rates. The process works in 2 stages, and both are strange. First, 2 helium nuclei collide and briefly form an unstable beryllium-8 nucleus. This nucleus is desperately unstable. It normally decays back into 2 helium nuclei within a tiny fraction of a second, roughly 1/10 quadrillionth of a second. But at sufficient temperatures and densities, a 3rd helium nucleus can strike this short-lived beryllium before it falls apart, forming stable carbon-12. The whole event depends on a remarkable coincidence in nuclear physics, a resonance in the carbon-12 nucleus predicted by astronomer Fred Hoyle before it was experimentally confirmed. Without this specific resonance, carbon would barely form in stars, and the universe would contain almost none of the element that forms the backbone of all known life. Helium burning produces less energy per unit mass than hydrogen burning. The star moves through this phase more quickly, consuming its helium reserves over perhaps 1 million years, rather than the 10 to 15 million that hydrogen burning required. When the helium is spent, a core of carbon and oxygen remains, surrounded by a shell still burning helium, surrounded by another shell still burning hydrogen, surrounded by the vast convective envelope stretching to the distant photosphere. The star has begun building its onion. As the carbon-oxygen core contracts further under gravity, temperatures climb toward 500 million Kelvin. At this extraordinary heat, carbon nuclei begin fusing together, producing neon, magnesium, and sodium through reactions that release both electromagnetic energy and ghostly particles called neutrinos. These neutrinos are important because they behave unlike anything else the star produces. They barely interact with matter at all. While photons take thousands of years to random walk from the core to the surface, neutrinos pass through the entire star in seconds as if it were not there. They escape into space immediately, carrying energy away from the core without heating the surrounding material. This neutrino energy loss becomes increasingly significant as the star progresses through its later burning stages. The core loses energy through two channels now: light that slowly works its way outward, and neutrinos that flee instantly. As heavier elements burn at higher temperatures, neutrino losses grow more severe, forcing the core to burn even faster to compensate. A feedback loop tightens. Higher temperatures produce more neutrinos, which steal more energy, which forces higher temperatures, which produce still more neutrinos. The core begins racing toward its end. A carbon burning lasts roughly 1,000 years. Then, the carbon is gone, and the core contracts again, heating until neon ignites. Neon burning takes just a few years. Then, oxygen ignites and burns for mere months. Each successive fuel lasts a fraction of the time its predecessor lasted. The compression between stages is dramatic. Millions of years of hydrogen burning, 1,000,000 years of helium burning, 1,000 years of carbon, a few years of neon, months of oxygen. The intervals collapse like a drumbeat, accelerating toward a final crash. And then comes silicon. Silicon burning represents the last act of nuclear fusion that can sustain a star. When core temperatures reach roughly 3 billion Kelvin, silicon nuclei begin combining through a complex web of reactions that ultimately produce iron and its neighbors on the periodic table. This final burning phase lasts approximately 1 to 2 days. Not years, not months. Days. Each day adds roughly 1/10 of a solar mass of iron to the growing core. The star has perhaps 48 hours of nuclear life remaining. The onion is now complete. If you could slice Stephenson 218 in half and examine its interior, you would find concentric layers arranged from heaviest to lightest, center to surface. At the very middle sits the iron core, surrounded by a shell of silicon, then oxygen, then neon, then carbon, then helium, then hydrogen, then the vast cool envelope stretching out past Saturn's orbit. Each layer represents a different epoch of nuclear burning, frozen in place like geological strata in a cliff face. The entire history of the star's nuclear life is written in these layers, from the gentle hydrogen burning of its blue youth to the frantic silicon consumption of its final days. But there is a critical difference between iron and every element that came before it. Every element lighter than iron releases energy when fused into something heavier. This energy is what powers stars. It is the source of all starlight in the universe. But iron sits at the peak of the nuclear binding energy curve. Iron 56, the most common iron isotope, has the highest binding energy per nucleon of any element. Fusing iron into anything heavier does not release energy. It absorbs energy. The star cannot generate power by fusing iron any more than you can power a car by driving uphill. Iron is the end of the road. It is nuclear ash in the truest sense. Every gram of iron that accumulates in the core represents material that will never again contribute to holding up the star. The core grows heavier while contributing nothing to the star's energy budget. It is a tumor growing at the heart of a giant, absorbing resources while offering nothing in return. Here is something that reveals how disconnected the outer layers are from the drama unfolding at the center. The enormous convective envelope of Stephenson 2-18 responds to events in the core on timescales measured by the sound crossing time, the time required for pressure waves to travel from center to surface. For a star this large, that timescale measures in years or even decades. The surface we observe today reflects conditions in the core from years ago. Information about the current state of the core has not yet reached the photosphere. The outer atmosphere continues its slow breathing, its gentle pulsation, its steady shedding of material into space, completely unaware that the core may already be in its final hours. There is an unresolved scientific question about whether the most advanced burning stages in Stephenson 218 have already occurred or are still in the future. We observe the star as it was 20,000 years ago due to the travel time of light across the distance between us. The core could be burning silicon right now. It could have already collapsed. It could still be working through oxygen or neon. We simply cannot know. The finite speed of light creates a wall of ignorance that no technology can overcome. The present state of this star is hidden from us as completely as the future is hidden from everyone. What we do know is that the iron core will eventually cross a threshold that nothing can prevent. A boundary in physics that carries the name of one of the greatest minds to ever study the death of stars. And when that threshold is crossed, the largest star in the universe will begin to die in a way that makes its enormous life look quiet by comparison, before we witness the death that awaits Stephenson 218. We must step back and consider a question that scientists have debated for decades. Is this truly the largest star in the universe, or simply the largest we have managed to find and measure? The answer is less certain than you might expect, and the contest for the crown of largest star has a long and complicated history filled with revised measurements, disputed distances, and surprising reversals. Stephenson 218 did not always hold this title. Other stars wore the crown before it, and some astronomers still argue about whether it deserves to wear it now. The measurement of stellar sizes at cosmic distances is extraordinarily difficult, and the numbers change as technology improves and methods are refined. Understanding this ongoing debate reveals something important about how science actually works. Not as a collection of fixed facts, but as a living process where answers shift as our ability to ask questions grows sharper. For many years, the title of largest known star belonged to VY Canis Majoris, a red supergiant located approximately 3,900 light-years from Earth in the constellation Canis Major, the Great Dog. This star dominated popular science discussions throughout the early 2000 years. Countless documentaries featured it. Educational websites declared it the undisputed champion. Estimates of its size ranged as high as 2,000 solar radii, making it seem comparable to what we now measure for Stephenson 218. But science does not stand still. As measurement techniques improved and the Gaia spacecraft provided better distance estimates, the numbers for VY Canis Majoris began to shrink. The star turned out to be somewhat closer than originally thought, which meant its physical size had been overestimated. More recent comprehensive analyses place VY Canis Majoris around 1,400 to 1,500 solar radii. Still enormous by any reasonable standard, still larger than the orbit of Jupiter, but clearly smaller than the central estimates for Stephenson 218. The former champion had been dethroned not by discovering a new star, but by measuring the old one more carefully. VY Canis Majoris remains fascinating for other reasons. It displays some of the most spectacular circumstellar structures ever observed around a dying star. Massive arcs and loops of ejected material surround it, glowing in infrared and radio wavelengths, evidence of violent mass loss episodes over the past 1,000 years. The star is visibly tearing itself apart as it approaches death, but size alone is no longer its claim to fame. Another contender held the crown briefly after VY Canis Majoris was revised downward. Scutum located about 5,700 light-years from Earth in the same constellation as Stephenson 218, was declared by some measurements to be the largest known star. Early estimates suggested dimensions approaching 2,000 solar radii, potentially rivaling or even exceeding Stephenson 218. For a period in the mid-2010s, Scutum appeared in many articles and videos as the undisputed record holder. Then came better data. Improved distance measurements from the Gaia spacecraft suggested that Scutum lies somewhat closer than originally calculated. When you reduce the distance to a star while keeping its apparent angular size the same, the calculated physical size decreases. Updated analyses now place Scutum around 1,700 solar radii. Impressive, larger than most red supergiants, but no longer competitive for the top position. Like VY Canis Majoris before it, Scutum was not replaced by a bigger discovery. It was simply measured more accurately and found to be smaller than we thought. A third competitor still lingers in the scientific literature, creating genuine uncertainty about whether Stephenson 218 truly holds the record. NML Cygnus, located approximately 5,300 light-years away in the constellation Cygnus, the Swan, displays properties that make some researchers wonder if it might rival or even exceed Stephenson 218. Some measurements hint at radii approaching 2,000 solar radii, though the uncertainties remain large. The star is heavily obscured by its own ejected material, making distance and size calculations particularly difficult. The debate over NML Cygnus versus Stephenson 218 continues quietly in technical journals, far from the confident declarations of popular science articles. Different research groups using different methods arrive at different conclusions. Some analyses firmly place Stephenson 2-18 on top. Others suggest the gap between the two stars falls within measurement uncertainty, making it impossible to declare a clear winner. The honest scientific position is that Stephenson 218 is probably the largest, but the word probably carries real weight. It is not merely polite hedging. It reflects genuine limits in our ability to measure these extreme objects. What makes these measurements so difficult? Several factors combine to create uncertainty that may never fully disappear. First, as we explored earlier, red supergiants pulsate. They expand and contract over periods of years, meaning their size depends on when you happen to observe them. A star caught at maximum expansion will appear significantly larger than the same star caught at minimum. Without monitoring each star continuously for many years, we cannot know whether a given measurement represents its average size, its maximum size, or something in between. Second, red supergiants lack sharp edges. Their atmospheres fade gradually from thin stellar material into even thinner circumstellar gas. Where exactly does the star end? Different researchers using different definitions of the stellar boundary will calculate different sizes for the same star. The photosphere, where the star becomes opaque, serves as the standard definition. But for stars this diffuse, even the photosphere is a fuzzy, shifting concept rather than a hard line. Third, distance measurements remain imperfect even with Gaia. Stars embedded in thick dust clouds produce position measurements with more noise and uncertainty than stars in clear lines of sight. The parallax shifts that reveal distance become harder to measure, precisely when dust scatters and distorts the light along its journey. Different teams analyzing the same Gaia data sometimes arrive at different distance estimates, which directly translate into different size calculations. Here is a strange possibility that occasionally surfaces in discussions among stellar astronomers. What if the largest star in the galaxy is one we have never detected at all? The Milky Way contains perhaps 5 million red supergiants at any given moment, We have characterized the sizes of only a few thousand with any precision. The most obscured regions near the galactic center remain poorly surveyed even at infrared wavelengths. Somewhere behind dust clouds thicker than those hiding Stephenson 218, a larger star might burn undetected. We have no way to rule this out. The record could stand for centuries, or it could fall next month when a new survey peers into a previously unexplored region. Some researchers have speculated about theoretical limits on how large a red supergiant can grow. Models of stellar structure suggest maximum radii somewhere around 2,500 to 3,000 solar radii for stars with optimal initial masses and mass loss histories. Stephenson 2 to 18, at roughly 2,150 solar radii, approaches but does not exceed this theoretical ceiling. The agreement between observation and theory suggests our understanding captures the essential physics. But theoretical limits carry their own uncertainties, built on assumptions about mass loss rates and convective behavior that may not perfectly match reality in the most extreme cases. What remains undisputed is that Stephenson 218 consistently appears at or near the top in every comprehensive comparison. Multiple independent measurements using different techniques converge on dimensions exceeding 2,000 solar radii. The star may not hold the crown forever, but it holds it now, and no current rival has clearly taken it away. But none of this matters to the star itself. Stephenson 218 does not know it is the largest. It does not care about rankings or records or the debates of distant astronomers. Deep in its core, far below the bloated atmosphere and the zones of nuclear ash, something far more important is happening. An iron core is growing, pressing toward a threshold that will end all records, all measurements, all observations of this star as a living object. A threshold named after a young physicist who understood stellar death better than almost anyone who ever lived, deep inside the largest known star, in a region no light will ever escape to show us. A ball of iron grows heavier with each passing hour. This iron core is the final product of 20 million years of nuclear burning, the last ash from a furnace that has consumed hydrogen, helium, carbon, neon, oxygen, and silicon in turn. Unlike every fuel that came before, iron cannot be burned to release energy. It is the end of the nuclear road, and it is about to trigger the most violent event this star will ever experience. The iron core of Stephenson 218 probably contains between 1.5 and 3 solar masses of material, compressed into a sphere roughly the size of Earth. This seems small compared to the star's overall dimensions, a planet-sized ball hiding inside a body that could swallow Saturn's orbit. But what this core lacks in size, it makes up for in destiny. Everything that happens next depends on what occurs within this dense central region. For now, the core is held up against its own crushing gravity by a strange quantum mechanical effect called electron degeneracy pressure. To understand this, you need to know something peculiar about electrons. They refuse to be squeezed too close together. This is not because they repel each other electrically, though they do. It is because of a deeper law of nature called the Pauli exclusion principle, which forbids any 2 electrons from occupying the same quantum state in the same location. As gravity compresses the core, electrons are forced into increasingly cramped conditions. They push back, not through any ordinary force, but through the fundamental quantum mechanical prohibition against identical particles sharing the same state. This degeneracy pressure is powerful. It holds up white dwarf stars indefinitely, allowing them to persist for billions of years after their nuclear fires have died. In the iron core of a massive star, it provides temporary support while silicon burning continues adding more iron to the pile. But there is a limit. a threshold beyond which even quantum mechanics cannot resist gravity. This limit carries the name of Subrahmanyan Chandrasekhar, an Indian-American physicist who calculated it in 1930 while still in his early 20s, traveling by ship from India to England to begin his graduate studies. The Chandrasekhar limit is approximately 1.4 solar masses. Below this threshold, electron degeneracy pressure can support a stellar core forever. Above it, gravity wins. When the iron core of Stephenson 2-18 crosses this boundary, the electrons that have been holding it up will be forced to merge with protons, converting both particles into neutrons and releasing a flood of ghostly particles called neutrinos. The support vanishes. The core begins to fall. What happens next unfolds with terrifying speed, compressing events that should take astronomical timescales into fractions of a single second. The core implodes, not slowly, not gradually. It falls inward at roughly 1/4 the speed of light, 75,000 kilometers per second. At material that was spread across a volume the size of Earth compresses into a sphere perhaps 20 kilometers across within less than 1 second. A region wider than our planet becomes a ball smaller than a city in the time it takes to draw a single breath. To grasp this compression, imagine squeezing Earth down until it fits inside the boundaries of a small town. All the mass remains, every mountain, every ocean, every grain of sand. But the volume decreases by a factor approaching 1 billion. The density in the collapsing core reaches and then exceeds the density of atomic nuclei themselves, roughly 200 trillion grams per cubic centimeter. A teaspoon of this material would weigh hundreds of millions of tons, more than all the cars, trucks, buildings, and ships ever built by human civilization combined. In a teaspoon. During this collapse, something extraordinary happens to the particles involved. Protons and electrons, crushed together by pressures beyond imagination, merge to form neutrons through a process called electron capture. Each such merger releases a neutrino, a nearly massless particle that interacts so weakly with matter that it can pass through entire planets without stopping. The collapsing core releases roughly 10 to the power of 58 individual neutrinos within a span of seconds. Written out, that number would fill a page with zeros. These neutrinos carry away the gravitational binding energy released during collapse, more energy than the star radiated as light throughout its entire 20 million year lifetime combined. For a brief moment, the neutrino luminosity of the collapsing core exceeds the combined light output of every star in the observable universe. Yet these particles are so weakly interacting that most pass through the surrounding stellar envelope without depositing any energy at all. They stream outward through billions of miles of stellar atmosphere as easily as light passes through empty space. They carry news of the core's death long before any visible sign appears at the surface. The initial implosion continues until the core reaches nuclear density, the point where individual neutrons and protons touch each other directly. At this moment, the strong nuclear force becomes relevant on a scale it has never operated before in this star's history. The strong force is what holds atomic nuclei together, but it only operates at extremely short distances, roughly 1 femtometer, a millionth of a billionth of a meter. When matter is compressed to nuclear density, particles are finally close enough for this force to matter, and the strong force has a crucial property. At very short distances, it becomes repulsive. You cannot squeeze neutrons together beyond a certain point because the strong force pushes back with tremendous power. This repulsion halts the collapse suddenly, like a rubber ball dropped onto concrete. The infalling material bounces off this newly formed neutron star core, converting the kinetic energy of infall into the kinetic energy of outward expansion. A shock wave is born. Here is something that puzzled physicists for decades. The bounce shock carries enormous energy, a roughly 10 to the power of 51 ergs, about 1% of the total gravitational energy released. You might expect this shock to simply blast outward through the star and create the supernova explosion we observe. But it does not work that way. The shock stalls. The overlying layers of the star absorb its energy by breaking apart heavy nuclei into their constituent protons and neutrons. Each ion nucleus the shock encounters requires energy to disassemble, robbing the shock of momentum. Within roughly 100 milliseconds, the shock stalls at a radius of perhaps 100 to 200 kilometers, far short of the stellar surface. For years, computer simulations showed this stalling problem with no clear solution. The shock would die, the star would collapse entirely into a black hole, and no visible explosion would occur. Yet real supernovae clearly explode. Something was missing from the models. The answer involves those fleeing neutrinos. Although they interact incredibly weakly with matter, the densities in the region behind the stalled shock are so extreme that even weakly interacting particles deposit significant energy. Perhaps 1% of the outgoing neutrino flood gets absorbed in a layer just outside the newborn neutron star, heating this material and providing the energy needed to revive the shock. This neutrino heating mechanism remains an active area of research. Three-dimensional simulations reveal that turbulent convection and chaotic instabilities play crucial roles, helping channel neutrino energy into shock revival. The explosion mechanism is far messier than simple spherical models once suggested. Asymmetric flows, swirling motions, and random fluctuations all contribute. Some simulations show shock revival. Others show continued collapse into a black hole. The outcome appears to depend sensitively on conditions that are difficult to predict precisely. There is an unresolved scientific question about what remnant Stephenson 218 will leave behind. If the neutron star mass remains below roughly 2 to 3 solar masses, a stable neutron star will form. If the mass exceeds this threshold, not even neutron degeneracy pressure can resist further collapse, and a black hole will result. The boundary depends on the equation of state of nuclear matter at extreme densities, a relationship that physicists still do not fully understand. The fate of the largest known star hangs on physics that remains beyond our complete grasp. But whether neutron star or black hole, the shock will eventually revive. And when it does, it will begin a journey outward through billions of miles of stellar envelope. The last light of Stephenson 218 will begin its long climb toward the surface. Once the shock revives, it begins a journey that no human will ever witness up close. The wave of destruction travels outward from the collapsed core, pushing through layer after layer of stellar material at speeds measured in thousands of kilometers per second. For a compact star like a blue supergiant, this journey through the envelope takes only hours. But Stephenson 218 is not compact. Its outer atmosphere stretches nearly 2 billion miles from center to surface. Even traveling at 10,000 kilometers per second, the shock requires many hours to cross this vast distance. During this journey through the envelope, something remarkable happens in the extreme conditions behind the shock front. Nuclear reactions occur that cannot happen anywhere else in the universe. The temperatures and densities are so extreme, so far beyond what exists in any normal stellar environment, that atoms are built in ways that steady nuclear burning inside stars could never achieve. Elements heavier than iron cannot be made through fusion that releases energy. We established this earlier. Iron sits at the peak of the binding energy curve. Anything heavier absorbs energy rather than releasing it. So where do gold, platinum, uranium, and all the other heavy elements come from? The answer is the supernova itself. In the chaos behind the shockwave, neutrons are captured by atomic nuclei faster than those nuclei can decay. This rapid neutron capture process, called the air process by nuclear physicists, builds heavy elements through a completely different pathway than normal stellar fusion. Imagine atomic nuclei absorbing neutrons one after another in rapid succession, growing heavier and heavier until they finally undergo radioactive decay and transform into stable heavy elements. This happens in milliseconds rather than the millions of years that normal stellar burning requires. Gold forms this way, platinum forms this way, uranium and thorium form this way. Every atom of these elements that exists anywhere in the universe was created in moments of extreme violence, like the one that will destroy Stephenson 218. The jewelry on your finger, if it contains gold, holds atoms that were forged in the death throes of massive stars that exploded before our solar system was born. The uranium that powers nuclear reactors was assembled in fractions of a second during ancient supernova explosions scattered across billions of years of cosmic history. These elements did not exist when the universe was young. They were manufactured by dying stars and scattered across space to eventually become part of new solar systems, new planets, new life forms. When the shock finally breaks through the surface of Stephenson 218, the supernova becomes visible to external observers. This moment, called shock breakout, produces a brilliant flash as the wave of destruction suddenly encounters the thin outer atmosphere and accelerates material to extreme velocities. The star brightens by factors of billions within hours, releasing radiation across the entire electromagnetic spectrum from radio waves through gamma rays. Because Stephenson 218 has such an extended diffuse atmosphere, the shock breakout will look different than it would from a more compact star. The brightness will rise relatively gradually as the shock pushes through the outer layers, rather than appearing as a sharp, sudden flash. The extended envelope spreads the breakout signal across time, smoothing what would otherwise be an instantaneous burst into a more drawn-out brightening. At peak luminosity, the supernova from Stephenson 218 will reach several billion solar luminosities. For a period of days to weeks, this single dying star will outshine every other star in the Milky Way combined. Our galaxy contains perhaps 400 billion stars, yet one explosion will temporarily produce more light than all of them together. The universe does not do anything by half measures when it comes to stellar death. From Earth, 20,000 light-years away, the supernova might briefly become visible to the naked eye despite the enormous distance. The intervening dust that currently hides the star will still absorb much of the visible light, but the sheer energy of the explosion may punch through regardless. In infrared wavelengths, where dust is more transparent, the event will be spectacular. Every infrared observatory on Earth and in space will turn toward this cosmic firework. The explosion will be classified as a Type II supernova based on the presence of hydrogen in its spectrum. The extended hydrogen-rich envelope of the red supergiant ensures that hydrogen dominates the outer debris, producing characteristic signatures that distinguish these explosions from other types that occur in stars which have already lost their hydrogen layers. The neutrino signal from the collapse will arrive at Earth several hours before any visible brightening. Because neutrinos escape the core immediately, while light must wait for the shock to traverse the entire envelope, these ghost particles carry advance warning of the impending display. Modern neutrino detectors around the world are connected through the supernova early warning system, designed to provide exactly this kind of advanced notification. When detectors register a sudden flood of neutrinos from a galactic supernova, alerts will go out to observatories everywhere, allowing them to point their telescopes toward the event before visible brightening begins. When supernova 1987A exploded in the Large Magellanic Cloud, roughly 168,000 light-years away, detectors worldwide registered a total of just 25 neutrinos. 12 were captured by Kamiokande, 2 in Japan, 8 by the IMB detector in the United States, and 5 by the Baksan detector in the Soviet Union. That detection, involving just a handful of particles from an extragalactic explosion, confirmed theoretical predictions about neutrino production in collapsing cores and eventually contributed to a Nobel Prize in Physics. For a galactic supernova like the one Stephenson 218 will produce, modern detectors would register thousands or even tens of thousands of neutrino events over roughly 10 seconds. The material ejected by the supernova will expand outward at velocities reaching 10,000 kilometers per second or more. For comparison, the fastest spacecraft humans have ever built travel at roughly 20 kilometers per second. The supernova debris moves 500 times faster. This material includes the hydrogen and helium layers that form the extended red supergiant atmosphere, the products of nuclear burning in various shells, and the heavy elements synthesized during the explosion itself. The expanding debris will sweep through surrounding space for thousands of years, glowing as shock-heated gas radiates energy at X-ray, optical, and radio wavelengths. Future astronomers will study this supernova remnant the way we study the Crab Nebula today, a remnant from a supernova observed by Chinese astronomers in the year 1054. Nearly 1,000 years later, the Crab Nebula still spans roughly 11 light-years across and continues expanding. The debris from Stephenson 2-18 will create a similar structure, a glowing memorial to the largest known star that will persist for millennia. At the center of this expanding debris will sit whatever remains of the collapsed core. If the remnant mass falls below roughly 2 to 3 solar masses, a neutron star will form. This city-sized ball of neutrons will be born spinning rapidly, perhaps tens or hundreds of times per second, due to conservation of angular momentum during collapse. Strong magnetic fields, a trillion times stronger than Earth's field, will thread through its surface. If the rotation axis and magnetic axis are misaligned, beams of radio waves will sweep through space like lighthouse beams, potentially detectable as a pulsar. If the remnant mass exceeds the threshold for neutron star stability, a black hole will form instead. The core will continue collapsing past the point where any known force can stop it, creating a gravitational pit from which nothing can escape. Not light, not matter, not information of any kind. The largest known star will become one of the most absolute objects the universe can create, a region of space-time where the ordinary rules simply end. Here is a haunting possibility. The light from Stephenson 218's supernova may already be traveling toward us. The core could have collapsed thousands of years ago, while humans built pyramids or wrote the earliest stories. Those ancient photons would currently be racing through interstellar space, 20,000 years into their journey, but still thousands of years from arrival. Or the collapse may lie in the distant future, with the star continuing to burn through advanced fuels for ages to come. We cannot know. The finite speed of light creates an absolute barrier between us and the present state of this distant giant. What we do know is that the death of Stephenson 218 will seed the universe with the raw materials for future creation. And in that seeding lies a connection to everything we are. The debris from Stephenson 218's death will not simply float through space as a monument to destruction. It will become something else, something that connects the death of the largest known star to the existence of everything you have ever touched, tasted, or loved. Because the elements scattered by supernovae do not stay scattered forever. Over millions of years, they mix with the interstellar medium, blending into the vast clouds of gas and dust that drift between the stars. And from those clouds, new stars are born. New planets form. New possibilities emerge. This is cosmic recycling on a scale that dwarfs any human concept of renewal. The iron in your blood was forged in the core of a massive star that exploded before our solar system existed. The calcium in your bones came from a supernova that detonated billions of years ago in some distant region of the galaxy. The oxygen you are breathing right now, every single atom of it, was manufactured inside a star through the fusion of carbon and helium. None of these elements existed when the universe was young. They were all created inside stars and scattered by stellar death. You are made of stardust. This phrase has become almost commonplace, repeated so often that its meaning can slip past without landing. But sit with it for a moment. The atoms comprising your body have histories spanning billions of years. They were processed through multiple stellar generations before assembling into the form you currently inhabit. Some of the atoms in your hand may have passed through 2 or 3 different stars, each time being incorporated into a new stellar body, each time being scattered again by explosion or stellar winds. When Stephenson 218 eventually dies, the heavy elements currently being synthesized in its core, along with those produced during the explosion itself, will join this cosmic flow. In perhaps 1 billion years, material from this supernova will have mixed thoroughly with surrounding gas clouds. Those clouds will collapse to form new stars. Some of those stars will have planetary systems. On some of those planets, the heavy elements from Stephenson 218 will become components of rocks, oceans, atmospheres, perhaps even components of living things, creatures that will never know the name of the star, whose death provided the raw materials for their existence. This connection runs both ways through time. We are connected to ancient stellar explosions through the atoms we carry. And we are connected to future possibilities. Through the atoms, we will eventually return to the cosmos. Nothing is truly destroyed. Nothing is truly created. Everything is transformed, recycled, reimagined across timescales that reduce human life to a brief flicker. Yet that flicker matters. It is the moment when atoms become aware of their own history. It is the instant when Stardust looks up and wonders about the stars. Future telescopes may find something larger than Stephenson 2-18. The extremely large telescope, with its 39-meter mirror, will peer into regions of the galaxy currently beyond our reach. The giant Magellan telescope and the 30-meter telescope will add their light-gathering power to the search. The James Webb Space Telescope continues surveying infrared sources with sensitivity that would have seemed impossible just decades ago. The Nancy Grace Roman Space Telescope, when it launches, will map vast areas of sky at wavelengths that pierce through cosmic dust. Somewhere in the unexplored regions of our galaxy, hidden behind dust clouds thicker than those concealing Stephenson 218, a larger star may wait. We cannot know until we look. The current record could stand for centuries, or it could fall within the decade. Each new survey that fails to find something larger strengthens the case that Stephenson 218 sits near the true physical limit of stellar size. Each discovery of a larger star would simply extend our understanding of what nature permits. The search will continue because searching is what humans do. We are creatures that seek to know. We measure the immeasurable. We reach toward the unreachable. We ask questions that have no practical value, driven by a curiosity that seems almost unreasonable when viewed against the struggles and demands of daily life. Why does it matter that the largest known star burns 20,000 light-years away? Why should anyone care about the dimensions of an object they will never visit, never touch, that never experience directly except through faint infrared light captured by distant telescopes? Perhaps it matters because understanding expands what we are. Perhaps it matters because knowledge of the cosmos places human concerns in a larger context, reminding us that we are part of something vast and ancient and ongoing. Perhaps it matters simply because beauty exists in knowing, regardless of any practical application. The universe does not owe us utility. It offers wonder, and we choose whether to accept. Tonight, as you rest, Stephenson 218 continues burning. The largest known star in the observable universe glows with the power of 400,000 suns, invisible to your eyes but present nonetheless. Its outer atmosphere pulsates slowly, yet expanding and contracting over cycles measured in years. Material streams outward from its surface, joining the interstellar medium, beginning the long journey toward possible incorporation into future worlds. Deep in its core, nuclear burning continues through stages that will eventually lead to iron, collapse, and explosion. The light you would see if you could observe this star tonight actually left its surface around the time humans first crossed into the Western Hemisphere, roughly 20,000 years ago. Those ancient photons traveled through space while civilizations rose and fell, while languages were born and forgotten, while countless generations lived their entire lives without ever knowing that such a star existed. Now, those photons reach telescopes operated by scientists who have dedicated their lives to understanding what they reveal. There is something quietly miraculous about this. Atoms that were forged in ancient stellar explosions have assembled themselves into creatures capable of understanding stellar explosions. The universe has become conscious of itself through beings living on a small planet orbiting an ordinary star in an unremarkable corner of an average galaxy. That consciousness now extends to encompass the largest known star, to measure its dimensions, predict its fate, and place it within a coherent story of stellar birth, life, and death. The story does not end with Stephenson 2-18. It continues with every new observation, every refined measurement, every question that leads to another question. The largest known star is simply the current boundary of knowledge, a marker that will eventually be superseded by future discoveries or confirmed as a true limit by continued observation. Either outcome adds to understanding. Either outcome extends the reach of human awareness into the cosmic dark. For now, the star burns. It has burned for 20 million years, and it will burn for perhaps a few 100,000 more before the final collapse. On the timescale of stars, this remaining lifetime is brief. On the timescale of human civilization, it is essentially forever. Countless generations will live and die, while Stephenson 218 continues its slow journey toward destruction. Your great-great-grandchildren's great-great-grandchildren may still look toward Scutum and know that somewhere behind the dust, the largest known star persists. Let that thought settle gently as the rhythm of these words slows. The cosmos holds wonders beyond counting, but you do not need to count them all tonight. The largest star will still be there tomorrow. The questions will still wait for answers. The universe will continue its patient unfolding whether you watch or rest. Feel the weight of your body against whatever surface supports you. Notice the rhythm of your breath, the gentle rise and fall that connects you to the atmosphere of this small world. The oxygen entering your lungs was made in stars. The iron carrying it through your blood was made in stars. You are woven from cosmic thread, a brief pattern in a fabric that spans billions of years. The largest known star burns tonight, 20,000 light-years away. And here, on this tiny world, surrounded by atoms that have traveled through space and time to become you, there is permission to rest. The cosmos does not require your vigilance. It asks only that you exist, that you wonder when you can, and that you find peace when wonder gives way to sleep. Close your eyes. The stars will keep their ancient watch. The night settles softly now, and the vast distances we have traveled together begin to fold gently inward. Somewhere far beyond the reach of sight, the largest known star continues its slow cosmic breathing, unaware of the small creatures on a distant world who have learned to measure its impossible dimensions. The atoms in your body remember their stellar origins, even if your waking mind does not. Let that connection hold you as sleep approaches. You are not separate from the stars. You are their children, their witnesses, their way of knowing themselves. Rest now. The universe will still be there when you wake, filled with wonders waiting to be understood. But that is for tomorrow. Tonight, there is only stillness, only breath, only the quiet privilege of existing in a cosmos vast enough to contain both the largest star and the smallest dreamer.